Plus, people like Syria just scared to come to Yeah, so she was wondering if you could have some time, but I think it's tomorrow morning or Thursday, Friday morning. All right. Okay, I'm making sure to get all of your fancy orders. I don't think I can do all of them. No. What is this? Oh, the Casa de Doctor. The honorable visit and honorable doctor. But they sent me. Yeah, I saw the connection. Yeah, but it was great. It was awesome. And I basically, I kind of understood your talk. Yeah, with enough French.
So you have joint papers with both of us, right? You have papers with both of us. Yes. Anyone else? We're trying to see from here. Huh?
From
yeah. Trying to compute the distance to zero.
No, but we have a joint center with Antonio without any students.
Yeah, nobody.
No. We have it with a student. And Antonio was driving the guy crazy because he was being shabby in diagrams and do you remember? And Antonio wanted illustrators.
I used to have that fight with some students.
And also, I was a hanger on I had taken
no, it has a lot of, it has at least 100 citations.
Oh, yeah.
Your paper has more citations.
Yeah, and it's still growing. It's the only pretty learning paper. It's the only pretty learning paper that is still growing. It hasn't gone down.
If I had my cards together, I should have.
We started. So what is this? That's true, but this that's also the other word. Oh no, she's I'm convinced that she's your strong advocate for keeping the
That part is right.
I mean, some of the things that could interpret some of the things don't advocate. If it's like an edit and an as thing, you say, okay, don't like create a department.
That idea is fun. I think it's
Sure, but don't forget about the report.
you don't know, you have to do all the
All right, I think you were the start.
the only one.
Yes. All right, ladies and gentlemen, Professor Malik, we are super happy to have one of my most favorite scientists of all time come to give a talk. Antonio Torralba is a professor and chair of this new department at MIT called AI and Decision Making department. They split from 2 departments, now they have 3. And Antonio is the inaugural chair of that 3rd department. Antonio is, of course, Division. I'm sorry. Division. Yes. He is. He's he comes from little town of island of Mallorca in Spain, but for some reason he decided to leave that paradise. He did his undergrad in Barcelona, and then he did his PhD in Grenoble in Paris, in France. And then he was a postdoc at MIT, and after long trials and tribulations, he became a professor at MIT. He has a gazillion different awards. The most, the latest one is the Thomas Huang inaugural award. He's the inaugural recipient of the Thomas Huang PAMI TC award at I think last year CPR, and lots of other honors. But really, for me, Antonio is like, like he is definitely the top person of his generation, which is also my generation. And if you can think of, if you think of our generation being, no, the generation was like, it was a great generation, and we were like painters in Renaissance Florence, okay? And there's lots of wonderful painters in Renaissance Florence. And then there is Leonardo da Vinci. Because some people are wonderful coders and wonderful kind of creators of algorithms. Other people create new ideas and new directions. And third kind of people are all about philosophy. And we're all good at our little business. Antonio is good at all of it. He codes with 2 Red Bulls still, 20 years on. He still codes with 2 Red Bulls. He creates new directions and new ideas. And it's wonderful to talk to him about philosophy of science and AI. And it's the thing is that what Antonio is doing now is going to be big in a decade. So you have to watch to see what he is doing now. One example, when everybody was doing graphical models in early 2000s, what did Antonio think? No, it's all about data. It's all about data, and nobody, of course, listened. Then finally, in the late 2000s, people said, okay, maybe we'll do some data sets. Let's do like 100, 10,000 images, maybe 100,000 images. And Antonio's like, no, 80 million images. This is 80 million more than ImageNet still, right? Oh, sorry, 80 times more than ImageNet. ImageNet is 1 million. And you never heard of that 80 million data set, but I'm sure you have heard of CFAR. CFAR 10 and CFAR 100. What is that? CFAR is basically machine learning people thinking, well, 80 million is too much. Let's do it 100 categories from that, and we'll call that CFAR. Okay, so Antonio knew ahead of time the importance of data, and it took the Canadians, 20 years to catch up. And
this is being recorded.
Yes. And just most recently, another complaint about Antonio, oh, but your images are only 32 by 32. Well, guess what? You look at DALL-E, you look at all these other image generation images. What is the resolution that they generated? 32 by 32. Because Antonio showed that 32 by 32 is enough. And this goes on and on and on. So I highly recommend you look at Antonio's papers from 10 years ago, and they're about to become big. So so now this is your chance to be like 2 decades ahead of the curve. With that, the great Antonio Torralba.
I think you should keep talking, and we skip the talk. Okay, well, that was embarrassing. I think that nothing I can do now will top that. So, okay, I'm going to try.
It's only downhill from here.
Yeah, now it's just downhill, okay? Okay. Yeah. Okay, well, there is no surprise. Computer vision has become kind of data crazy. We already know that. Alyosha has already explained some of it. And data sets are becoming like so large. They are going from large to huge. Like now it's insane. No, it's all of the data is in the data sets. There is nothing else out there. It's just amazing. One of them actually is not very big, but maybe only one of you knows about it.
Yes.
Okay, but first I wanted to give you an update on my mother's work. she knew this dataset business was going to be important. She's been labeling images since 2007. Okay, this is 2022. She still labels images. Every single day, she'll put a few hours. She's probably labeling right now as we speak. And she's been labeling like crazy. And I just wanted to give you a little bit of an update of what she's been up to in the last months. So she's been labeling all kinds of images. These are images that she has labeled. But recently, she learned about ImageNet, and then she thought, okay, just let's label ImageNet. And she's been segmenting objects in ImageNet with parts and everything. And it's just becoming crazy. It's just labeling the whole thing. But one of the interesting things also is that, okay, my mother is labeling a lot, but eventually ImageNet is just too large to get it labeled. So, GANs, on the other hand, are becoming really, really good at drawing images that look very realistic. And people have shown that you can take, cars, and you train, with a style GAN, and these are images that are rendered with the GAN, and it's just so amazingly good quality. And the hypothesis that we had, and this was work in collaboration with Sanya Fiedler's group, was that, okay, if the GAN can render it, it knows what it is. So can we use this GAN that already knows how to render these beautiful images to generate a dataset that will be fully annotated? So basically, we want to kind of generate, a GAN model dataset that you sample from it, and it already gives you all the images already fully annotated. So this is the idea. Just start with a GAN that you have already trained to generate images that look very realistic. And you know that the internal representation must know something about the objects that it's rendering, because otherwise, how could it do it so well? And the hypothesis is that now, one thing that you can do is you take an image that has been rendered by the GAN, you annotate the objects that are being rendered. This is the only thing that the GAN doesn't really know. It doesn't know how to put names to things. That's what you know. So you annotate a few images, and you don't need to annotate a lot. And because now you can spread your budget, your time budget, instead of devoting it to annotating a lot of images, you can just put a lot of effort in just few images. And you can label them with excruciating detail, with all the different parts that it contains. And now what you do is you take these annotations, you also have the images that were generated by the GAN, which means that you also know what the internal representation was that generated those images, and you train a very shallow network that reads the representation and learns to decode the representation into segmentation. And what is really cool is that you don't need to have a lot of annotated images to do this. With just like 16 images, you get fairly good segmentations out. So once you have that label branch already trained, then you just sample from it. And the nice thing is that now it will generate images that are fully annotated. And they will be fully annotated with a lot of parts, whatever you gave as input during this annotation process, and it will just generate these really wonderful images with lots of details. And now you can generate a gazillion of them, and then use your favorite algorithm for object segmentation, mask CNN, or whatever you want to use, and just run the standard pipeline and run it with that dataset that is being generated. So now what we can do is we can take a GAN that generates, for instance, images from ImageNet. So this is the result of a conditional GAN that is being trained with ImageNet, and they look pretty good. I mean, the images are quite amazing, the images that get rendered despite of the diversity of ImageNet. And now what you do is you take ImageNet, you train the style GAN, or big GAN, whatever GAN you want to train. In this case, we train big GAN. You take my mother, you annotate a few images, and then that's it. You just sample from it, and you get a gazillion images. So that's what we are doing now, and this is what my mother has been focusing in the last months.
Where's her name on the author list?
Well, okay, so she actually is in the author list in several papers, but this one, unfortunately, when it was submitted, the students forgot to add her, and then because CVPR doesn't allow anymore to add authors, we couldn't add her. Yeah, but she is co-authoring like 4 papers. She has citations and everything. Like, it's just. There is a paper with 2 authors. Yeah. I have a paper just with her. My contribution was to translate from Spanish to English. And now, you can sample from this GAN. So here is, one of the classes with dogs, but they come with segmentations. No, it's a segmented data set, and you can do whatever you want. But this is still not addressing the problem of we are still dataset hungry, and here is just another way of generating a lot of data. Who cares about this? And in fact, just recalling Jitendra many years ago, at some point we had a conversation, and he was saying, everybody, yeah, sure, large datasets are interesting, but really, the interesting limit is not when n goes to infinite, but when n goes to 1, and then we had a discussion about this. And I think that time showed that n going to infinite was actually quite interesting. And what I want to say now is that he's still wrong. I don't think that n going to 1 is either very interesting. It's n equal to 0 that is really interesting. So that's what this presentation is about, is how do we make n equal to 0. So this is a collaboration with Philippe and Manel and Jonas and Tonsu, that probably you know several of them, because they've been here for a while. So that's what we wanted to do. Let's do n equals 0. So, okay, how do you train a system if you have no data? Okay, so this is the two things that generally you need in order to train a vision system. You need images and you need labels, whatever the labels are. It could be segmentations or categories, whatever you want to use. And the community has been working really hard in getting rid of labels. And in fact, it's been quite successful in the last few years. It's just amazing the amount of things that have happened that have shown that you can get really good visual representations with no labels whatsoever. And contrastive learning is one example, but there are many other, like autoencoders and so on. And you play these games where you try to learn a representation that will put examples that are similar close together, and because you don't have labels, the way that you do that is by generating virtual training examples that are just transformations of one single image, and you want all of those to project together, and then that should be different from other images, and just playing that game, it gives you visual representations that are pretty remarkable. So that's one thing that you can do. And what is nice is that now you have this network, you have to learn these weights you learn them with no labels whatsoever, and then at the end what people will do is this builds some visual representation. And the way that you check if your visual representation is good or not is that you train a linear layer that will translate that representation into a classification task and then check the performances. But you only train the last final layer. This visual representation will have to be able to translate your image into something that is useful. And it's quite remarkable how far this has gone. No? So most of the experiments I will show are going to be on ImageNet 100. Okay, this is a cheap version of ImageNet where we selected 100 classes instead of 1,000, because one of the issues is that we have these large data sets, and this is actually creating a problem for academia, because you have to run your experiments on these huge data sets, and it takes a lot of CPU and GPUs, and a lot of times you cannot run a lot of iterations. I think we went too far pushing for large data sets, and now we are paying the price, and we kind of have to push backwards and say, okay, let's define some benchmarks that are good enough. So, I think we need the help of everybody, because it's very hard to convince reviewers that this is interesting, because they say, well, what happens with ImageNet, with the full ImageNet? Well, what happens? Well, the same thing. It's just 10 times more data, but it's about the same thing. So anyway, it's a hard battle to fight. But this is, a small data set that will allow us to do a lot more experiments. So if you use contrastive learning in this data set and then use a linear classifier at the end to do this 100 classification task, the performances that you get is what I'm showing here. So this is a graph that I'm going to be filling with results. The vertical axis is performance. This is the performance that you get in this 100 classification task. So chance will be 1%. With different data sets. So when you use contrastive learning to learn, you can use data sets that are different from ImageNet. So if you use ImageNet itself, ImageNet 100, then you get around over 60% performance, 63 or so. But if you use the actual whole ImageNet, you get worse performance because you're adding new classes that you will never test, so it's slightly worse. And then if you use something like STL10, then you get even lower. But this is about the type of performances that you can get when you are learning that representation with real images. Okay. So this is contrastive learning on real images, and I'm going to build on this result for a while. Okay. So yes, you can get rid of labels, but that's not what I want to do. what I wanna do is really to get rid of the whole thing, okay? Because everybody complains about labels, annotation, and so on, but images is also a pain. There are so many issues with images. They take memory, you need to collect them, there are copyrights, privacies, there are biases, there is the whole thing, it's a mess. So really what I want is to get rid of the full thing. And this is what I mean by n equals 0. Because a lot of people, when they say n equal 1, really they are thinking about transfer learning or one-shot learning. And that, the visual system already knows a lot of things. No, this is about how do you learn to see if you have never opened your eyes, okay? How far can you go? Okay, so what can you do? You have, we want to find out what the weights here should be. And you are not allowed to use any data to train this. What do? Well, one simple thing that you can do is just put random weights, and that's it. That's it. That's your network. What happens if you do that? Well, if you put random weights, this is what you get. This is you get around over 20%, which is already much better than chance, much better than the state-of-the-art computer vision 15 years ago. For people that say, we didn't have compute to train anything, there was nothing to train, okay? You just put random weights and you were already above performance of computer vision 15 years ago. So anyway, there it goes, the need for compute. Okay, the nice thing about this project is we want to be able to do better than this without any type of real data. The nice thing about this project, it was kind of easy to convince the students because first, you only need to beat this, okay? As soon as you do anything, if you get higher than this, that's okay. That's already good. You don't need to get to the real data. This is going to be our upper bound. It's very difficult that we will be able to do anything better than this. But at least you should be able to get it better, do better than random weights. So this was a winning project for all possible metrics because whatever you did, it was going to be better than this. This is a fantastic type of project to do because you know that it's going to work no matter what. So this is, this is the range of performances in which we are going to be moving. And the question then is, what are the strategies that you will use in order to build those weights so that we climb this ladder and we get as far as possible and we'll see where we get.
Do you have any insight into why, with random weights, you get something non-significant?
I don't think...
It's got a linear layer on top.
Yeah, so there is a linear layer. But still, why is that even with the linear layer it works a little bit? I don't think no one really knows even why when you train it, it still works. So, I think it's okay. But I think that it's just that, you get a lot of features and they are kind of useful to some degree. So that is the best intuition I have right now. And actually another interesting thing is that what if you don't even want to train that linear layer? Like really the ideal test is a test where you don't have real data at all. You don't train anything whatsoever. And the best test is to do nearest neighbors. So how good is your representation as a similarity metric? Okay, so you have a network that has random weights, and we take like ImageNet 100. If I give you like these query images, and I look for the nearest neighbors in the metric given by the representation built by these random weights, how good are the neighbors? Okay, so let's look at them. Here there are the top 5 nearest neighbors for each query image, and okay, you can see it's pretty random. So there is some work to do. The color is kind of right, it's getting the colors right, but beyond that, there is really not a lot. These images, they don't match that at all. If you look at the, if you try to do classification with nearest neighbors just by looking at the category that has the most votes, the accuracy is around 4%. So it's just barely better than chance. Chance still will be 1%. So it's doing a little bit better than chance, but not by much. So it's a terrible, as a visual representation, it's really not very good. This is probably computer vision 15 years ago. So that's that's okay. That's okay. Okay, what else can we do? Okay, let's see. We cannot use real images. So the next thing that people immediately think is, well, let's use virtual environments. You can render images that try to imitate the world, and that's going to be great. Why not to do that? You're not using real images. Okay, that's fair game. But building these environments is a lot of work. And this talk is about maximum laziness, okay? So this is still too much work. And getting these things, is very complicated because you have this gap between simulations and real data that is always there, and at the end the performance is never matched, and it's just very tricky. And the problem is that you need to do a lot of work in order to get simulations that are very useful. So this is a video from Virtual Home that is one of the simulators that we created. And here is a person, it's an agent that you can control, and he wants to watch TV, so he takes the remote control with this strange pose. And now he's going to go to the couch and sit down. We have a poor placement of cameras. And now he wants to drink, and look at that. It doesn't know where the mouth is, okay? And in order to do simulations that are realistic, you need to get all these details right. And whenever there is something new that you want to simulate, then there are a whole kind of worms that gets open, and you need to get all these details and so on. So the gap to sim to real is just hard to close. So this talk is not about making that gap smaller. This talk is about making that gap huge, okay? We are going to make it really, really large. If we cannot make it small, then just go large, okay? So that's what that talk is going to be. Well, and there are a bunch of simulated worlds that you can use, like Minecraft, clever images, and actually, you use them to pre-train. It's not bad. You get some performances. Now, this is Minecraft, and it costs around above 40% here. It's pretty good. And Minecraft is images that are kind of very different from real images. But still, you learn some relatively good visual representations. But someone had to code Minecraft. It's just a lot of work. You have to create these environments, and the rendering engine is just a lot of work. We don't want to do any of that. So how do we reduce this sim to real group? Okay, gap, we are not going to reduce it. We are going to make it really, really large. And there is evidence that biology might be doing also something like that. So what is the type of simulations that biology will do in order to learn to perceive the world? So what you will see here is a video of recordings on the retina on an embryo, of a mice embryo. What happens is that the retina has some spontaneous activity and is generating a stimulation. And it might look like noise. It might look like noise. And this is what it looks like. So these are just different recordings of the retina, and you see these waves that move around, and they are called retinal waves. And one thing is, well, maybe this is just a spontaneous activity, but maybe it has a functional role. And what people believe is that, in particular, this type of waves might be useful for learning to do optical flow. So what we are saying is that, well, this type of simulations might be useful to learn to see before you open your eyes. What kind of representations will you learn if this is the type of things that you are allowed to see? And there is a paper actually that shows that if you use fractals, so just take images that are generated with these very simple generative processes that generate fractals, if you pre-train with these fractal images, you get performances that are above 30% in this task. They use it for pre-training a network and then fine-tuning. So here we are not doing any fine-tuning, and I'm totally against fine-tuning, so we can talk more about that. But here what they show is that you get some performance. Well, this is what we show because they show it only for fine-tuning, but you get some performance that is not too bad. And these processes, they look like nothing like natural images, but still not as good as Minecraft, but So what we wanted to see is if we could learn by looking at things that look like this. Just noise. Of course, this is an extreme view of noise, and the type of noise that we will use is just stochastic processes that generate some interesting patterns, but they are still noise. It's some sort of random process, but they will have some structure. So let me show you just some of the things that we will create at the end. So this is crops from images that we generate, and also crops from real images. So there are 3 that are real and 3 that are fake, that are the result of noise processes. And you have to guess which one is what. So I'll let you think a little bit about it, and then I'll show you which ones are real and which ones are fake. It's not super hard, but it takes a little bit of time. So let me show you. these are. So these ones here are actually noise processes that have a structure. So I'll explain in a moment how that structure works. And they generate patches that look a little bit like patches that you could find on natural images. So if you were training to see a visual, if you were learning a visual representation with those, you could get kind of far away. Okay, so now I'll give you a little bit of, we are going to go step by step in building different types of processes and see how well they are as data to train visual models, and that kind of will mirror a little bit the history of computer vision to some degree, or at least statistical image models. So one of the most interesting initial generative models of images were what was called the dead list model. This was a process that was introduced in the 60s, and then it became really popular in the 90s, and it was used to explain some of the properties that natural images have. It's a little bit of a toy of what a natural image is. And the way these processes work is, think of leaves falling on the ground. Leaves have different sizes, different colors. They fall on top of each other, creating occlusions. In this case, the leaves are just squares. And once they have fallen on the ground, they generate different patterns. And it's just the random process of selecting this distribution of sizes and which ones fall first and last, the order. It will create different types of images. And these images had a number of properties that were kind of similar to the ones that you find in natural images. Of course, they don't look like natural images at all. But there are a few things that are statistically similar to natural images. And they are very easy to produce. You need 1 million of those. It's very easy. Okay, I can give you 1 million of those. You can actually generate them on the fly. You don't even need to have the collection. You can just generate them on the fly as you are training. Here there are a bunch of them. So what happens if you use these images to pre-train your visual representation? Well, another thing that you can do is, this works with squares. Now you can put the squares in random orientations. You can also have leaves of different shapes, like circles and triangles and so on. So now what happens, if you take this just as your input data and now you train a visual representation with them. Well, this is what happens. So these are the 3 different types of deadlift models with only squares, with orientated squares, or with random shapes. And you can see that as you add more complexity, performances get going up, which is reasonable. And the deadlift models with random shapes, which is a very simple process, is really just shy of the performance that you get with Minecraft. And there is no 3D engine. No one had to encode complicated environments or anything. This is the dumbest model you can think of. And it's already midway in the gap between random training and full training with images. And the other nice thing is now, what happens as a visual similarity? So you have your input images. These are the same ones that I was showing before. What happens if I look for the nearest neighbors once you have trained your visual representation with these deadlift models? So these are the nearest neighbors. Well, it's pretty terrible still, But accuracy has gone up quite significantly. It's 12% now, if you look at the majority vote for which class gets represented there. This bird, it actually got 2 right, which is quite impressive. I mean, this is just seeing squares and circles, and this is how it's been pre-trained, and it's capable of locating these birds. Here is just a mess, maybe 1 image. But the parrot, it got 1 parrot. Maybe it's just pure luck, I don't know. But it's getting somewhere. Yes.
So the deadlift model, are there any parameters that you're tuning, or is it just no parameters at all?
The parameters could be things like the distribution of sizes that you have, how many.
Are you tuning them here or not?
No, there's no tuning. Yeah, there's no tuning. But you can explore the parameter set and so on.
So the amplitude spectrum is pretty close to natural images.
Yes.
That's the big advantage.
Yes. Okay. Talking about the amplitude spectrum. Here is one tool that probably many of you have never heard about, which is the Fourier transform. Can you raise your hands if you have heard? Only the first row. Okay. Believe it or not, this was the tool to use many years ago. Everybody working on image processing, of course. But even in computer vision, Fourier transform was very popular as a way of analyzing images. Yes. And there is still one remarkable property of natural images. If you take an image and you do the Fourier transform, you know, you don't know what it is. I'm just talking for the first row probably now, but it doesn't matter. Just believe me. There is.
We teach it.
You teach it. You teach it. Okay, some people are nodding, but
Learn it or not.
yeah. Okay, some people are saying yes, yes. Okay, okay, okay. One remarkable property is that if you take an image and you compute the Fourier transform and you look at the amplitude of the power spectrum. So this is this drawing here. It always looks like this. Most of the energy is concentrated on very low frequencies, and as you go to higher frequencies, which is what encodes the details on the image, the energy falls off very, very quickly. And in fact, it does it with this property that is called 1/f, that the amplitude of the energy that you have on this on different frequencies drops with the frequency, with the square of the frequency. And this is true for almost any natural image. In fact, I challenge you to take your camera, try to take pictures of things that will not have this property. And it's just amazingly difficult to find something that will not fit that. So, what can you do now? And in fact, people have been using this for all kinds of things, for explaining maybe how the retina actually encodes signal, why is that we have a particular structure in our retina. One of the hypotheses is just because it's trying to encode images that have this 1/f property in the power spectrum. Okay, so now we can use this to create images. How we do that? Well, you take some noise. Okay, probably you are more familiar with diffusion models than you are with this, okay? so think of a very small diffusion model, okay? that starts with a single, a noise signal. And what we are going to do is we are going to do the Fourier transform, impose the Fourier transform to have this amplitude. We keep the phase, and then you do the inverse of the Fourier transform, and it gives you an image. And it always looks like this, like clouds. Whatever you do, whatever image you have, you do this, always clouds, always. The only image that will preserve its identity under this operation are pictures of clouds. Okay? Okay, so this is the images that you get. So now the question is, well, we can create a gazillion of those, and you can change the slope. 1/f is true, but the slope of the there's always an exponent in f, and that exponent changes from one image to another. So we can just randomly sweep that in the range that we believe is the one that's discovered by natural images between 0.5 and 2. Just some random uniform distribution, and these are examples of images that you get. Okay, what happens now you train with this? So here is our plot of performances. Where do you think it will land? Any guesses?
Better than Minecraft.
Better than Minecraft? It's actually pretty bad. It's actually pretty bad. But 30% is way better than chance. But yeah, it's surprising that the list is actually better, no? But you have edges and so on, so it's pretty good. Yeah, you don't have edges here.
Did you try a scattering transform? It's also kind of inspired by natural laws.
Okay, let's get back to that in a second. Okay, another remarkable property of natural images, and this is kind of more related to the scattering transform, although not exactly that. Okay, another remarkable property is if you take an image and you compute the histogram of color values, of pixel values, of intensity values on an image, you get some histogram. There is nothing remarkable about it. There is no special structure, and that's just what it is. There's nothing interesting to it, okay? However, if you convolve your image with a zero mean filter, like for instance, computing a derivative of the image, just by taking pixel differences across nearby pixels. So in this case, it will be like a vertical edge detector, and you get this. Here, the gray represents 0. And what you see is that most of the image is 0, no? And there are a few places where you have high contrast, and probably you have seen this many, many times. And the remarkable thing is that if you do the histogram of this signal, it looks like that. And you see it's extremely uniform. It's just very clean. It's a very clean shape. It doesn't have all these peaks and goes ups and down. No, it's very, very clean. And if you do this for another orientation, you get the exact same thing. It's always a very clean shape. And it's almost true for almost any small zero mean filter. So you always get these things, and always very, very clean. Okay, so this is Bruno's old work. Just this property was enough to build some of the first models that were capable of reproducing receptive fields that look like anything that you find on the cortex. So this was kind of a, inspirational moment at the time. And then it also inspired a whole family of models for texture synthesis and analysis that Jitendra also did a lot of work on this type of modeling. But in particular for texture synthesis, there was this one on based on from Higer and Bergen, which is a okay. You can think of this. You are probably a lot more familiar with GANs and autoencoders than you are with this. So think of this as a GAN with a single encoder layer and a single decoder layer. Okay. I'm sure that like that you can understand it. And the way it works is you take one image, you go through your encoding network, which in this case is just one layer. It's just a bank of filters, the steerable pyramid, just filters that are oriented at different scales. And then the way that you represent that is just the histograms of those of all these outputs of all these filters. And then the synthesis consists in generating another image that fits the same histogram. Okay? So that's how it works. Okay, so how do we use this texture-based image model? You start with sigmoids, so going back to the diffusion model, but now there will be just a little bit more than just 2 layers. The first thing is you impose the spectrum to be 1/f. So we are going to combine all of the things that we have seen. Then you have your encoder that is going to be just the steerable pyramid, just a bunch of filters with different orientations. Then you impose that those filters should be sparse. So if this is Gaussian noise, once it's filtered by any filter, you always will get Gaussian noise. So this is not going to transform the histograms. It only scales them and changes the variance, but it's still Gaussian. So you need to do some nonlinear transform to get something that will look like a sparse, like this distribution that looks peaky at the origin. So you impose that. How do you do that? We are not allowed to use any learning. So we just use a simple prior on what the shape should be based on what we know about natural images. So the sparsity coefficient generally range also between 0.5 and 1.2 if it's not very sparse. So just something like that, just pick a random one number. And then you have your decoder, which is basically just taking this histogram and generating an image by collapsing the pyramid. And then you impose, we need also some color models. So what we will do is just use the color model that we had on the dead leaves model. So just take an image from the dead leaves and we want to match the same histogram of colors. That will create patches, but they will be very random patches. And that's what you get. And the only thing is that here, if you do this process once, it's not going to get what you wanted, because as you do all this, impose all these different properties, you break the other ones, so you just iterate this a few times. So now it really looks like a diffusion model where you have all these, bottlenecks. I'm sure that I'm getting you back. And this is what you get at the end, just some image that looks like nothing, but interesting, but like really nothing. And you can do this many, many times with different coefficients, and you get all kinds of random images that look somewhat more interesting than just dead leaves. Okay, so now we can use them to train. Where do you think this will land? What do you think will happen? You think it will be better than dead leaves or worse? There are some holes, no? So you have a hint. Okay, this is what happens. So this is if you only use the histograms. So it's just barely better than the spectrum. This is if you use the spectrum plus color, actually. So you use the power spectrum and just add the fact that you want to generate 1/f noise that has a color histogram that looks like this dead leaves model. That already increases performance quite dramatically, and that's because it forces to create patches of more or less uniform color. So it gets really close to the dead leaves model. But when you use the 3 things together, it actually gives pretty good performance, really, really shy of Minecraft. And this again is just very simple images to produce, really trivial. And you can actually use these textures in combination with dead leaves, and that gives you the best performance. Just like basically like Minecraft, okay? And you can play this game as many times as you want. Okay, what else can we do? Okay, let's look at the nearest neighbors. Here is, you have some input images, and these are the nearest neighbors. Accuracy went up quite a bit now. It's 28%. This is pretty good. And you can see some of the neighbors are really spectacular to me. I mean, the parrots is just basically the same thing. The lobster there, it got 4 of the lobsters. No, it's just and all kinds of poses. And this has never seen any natural image. It has never seen what a lobster is. And it's kind of capable of putting all these things together. Here, you have images of people. These people are eating lobster, but it just gets just images of people. And the birds here is just all kinds of different ones. So probably, ImageNet, by ImageNet standards, this is not a very good classification. But the visual similarity is quite kind of striking, no? And it has never seen images. Okay, what else can we do? Okay, we know that GANs are really good at generating images that look very real, no? So let's use GANs. And we know that if you train with real images, you can get things that look very realistic, but you cannot do that because you cannot use real images, okay? We cannot use real images for anything, not even to train GANs. So if you want to use a GAN, you can still not train it. That's the rules of this game, okay? So what can we do? Well, you could put random weights. Just take the GAN before training it and just sample from it, and let's see what happens. So I'll show you in a second what happens. Another thing that you can do is also to to put into the weights filters that look kind of what you would expect to learn, things that what happens if you untrain. So what are the filters? You can put some predefined filters. Now these are convolutions of 3x3, most of the kernels. So just put things that look like derivatives and Laplacians and so on, and you put it inside. You know that that's the type of filters that these models like to learn when they have natural images, so why not to put them? And now you can sample from it, and these are the type of images that you get. And they look relatively similar to the ones that I was showing before, but there are some other things that are happening here. Like if you look at them, they seem to have like more 3D-ness to them. It's not very. There is not really anything natural here. There is not a lot of structure, but there seems to be a little bit more complex than the ones that we were generating with the power spectrum and histogram statistics. They don't look as flat as the other ones did. So there is something different here. So now, when you train this with those images, this is what you get. You go much higher than Minecraft. The gap is really getting really small here, no? And this thing has never seen real images. This is a style GAN with random weights. No, it's actually not that very good. But if you initialize the weights with the right type of kernels, then things get quite good. And I'm sure that there are even better initializations. No,
Those filters are there because they made sense for the visual system.
That's fair game. I allow that. You are allowed to use your knowledge about what natural images are. You are just not allowed to use natural images. But it's okay. So you can say, yeah, but we are also like a GAN, It's okay, I cannot have a person that is untrained on this, so it's okay. I think that's fair game.
So, it's not really a GAN, it's just a generator from a GAN, right? You're not looking at the discriminator at all.
No, that's right. It was never trained, so there is no. It's just the architecture. There is no the GAN.
Filters are pretty good. Filters are like first derivative, second derivative.
Yeah.
We know those are good filters.
Yes.
He cheated by knowing Hugo.
That is something we use for decades.
Yes, and you are allowed to use the history of computer vision to decide what to do. So that there is. I'm just trying to bring back, the fact that what we did in the past was useful. Okay, that's what I'm trying to do. Yeah. Okay. So now, what is happening with the nearest neighbors? So here there are the images, and these are the nearest neighbors. The accuracy went up, but for these particular examples, I think that they actually went down. I don't like the neighbors so much, but it's okay. The performance went up to 33% overall, but it's just for these 5 examples that I picked, the quality is slightly worse. Here it's interesting to see that there are a couple of people actually eating lobsters, and you might think, okay, but this must be just fortuitous. No, I don't think it is. I think that there is something to it. In fact, when you train with ImageNet, you really will get only people eating lobster here. So it really is capable of doing that. And I think that it's just getting closer, but I think that the bird now got really bad, and before it was doing fine. Okay, what else can we do? Okay, so this is the game. No, we are trying to learn to look at by just looking at noise, and there is actually, we also know that these models now are getting quite popular. This strategy to train systems is getting popular in other domains. For instance, language is also showing that you can pre-train a model with random strings And these pre-trained models actually do something reasonable. It's not totally crazy. They are much better than chance. So there is something about these random structures that is interesting. So what else can we do? Well, there is another community out there that creates really beautiful visual displays with very simple scripts. And this is like, for instance, what is called like OpenGL fragment shaders, which is this particular example is one that has enough characters that will fit on a tweet. So you can tweet your code, and it should do something really beautiful. And there are some that are just amazing. So this is one example of one. If you run this, you get this beautiful image. And now the question is, well, this is not real data. How far can you go if you start training with these things? This is like the deadlifts model. You can think of a version of this. You can also write a script that will draw deadlifts models. So here there are a bunch of examples of short scripts, and the images that you generate. There are all kinds of things. It's really, really beautiful set of images. And they actually, if you test them one by one, just what you do is you run the shader, you collect like 10,000 images from them, and you train it. So these are the different performances that you get with images that come from each of those. This is just to show a little bit relatively the fact how it is in performance. The test is not completely fair because we are using 100,000 images to train each model here. This is only with 10,000 images, so this comparison is not valid. But it's just to get a sense of the fact that there are some shaders that work really well and others that are not so good. In fact, there is one that works really well, which is this one here, that produces just these amazing images, and it's just relatively short script. This is larger than a tweet, though, but it's still short, and it's around what deadlifts can do with much fewer images for training. So what we did is we collected 20,000 of those scripts. So now you have a huge data set that is like ImageNet, but with non-real images. It's all these different types of graphics. And now, you can run the same game that you have with ImageNet. You could run a classification task or, whatever you wanted to do here, but these images are non-real. So what happens if you do that? Well, here is trained with supervised contrastive learning because you have labels, but also you can play the contrastive learning game. So where do you think it will sit?
Wait, what are the labels?
So the labels here are just which shader produced those.
Shader, okay.
So where do you think it will sit? Okay, this question is really trivial. I left a hole here, so it will have to be here. But how close will go to real?
I can see the relation in the white.
Yeah, you can see that I made the white bar very. Here it is.
Whoa.
So it's really, really close to real images. Really, really close. Of course, this is in ImageNet 100. One thing that happens when you go to ImageNet 1K is that it's like a microscope. And it amplifies everything, and this gap becomes a little bit larger again. But it's the same ordering, everything the same, and the gap is really relatively small.
Hard-coded so much knowledge in this specific category. How many different shaders are there?
Well, in this case, we have 21,000.
So that's a lot of.
It is a lot of knowledge, but it's knowledge. It's not real images, so it's fair game. So we are not using the videos per se. I mean, we are using frames as if they were independent images, but you could use the videos and do cool things with the video. Here we are only using them as static frames.
Knowledge of the graphics researcher who is producing.
Yeah, there is, and some.
Who has looked at images?
Sorry.
The graphics researcher has looked at images.
Yes. But that's fair game. I think that's okay. That's okay. We can have a biological entity in the middle, okay? That's perfectly fine. Okay, what happens with the nearest neighbors? Accuracy goes to 43%, and these are the neighbors. I mean, and this is not a hand-picked set of neighbors. I mean, when we look at the whole thing, and they just look beautiful. Look at the parrots. It's even images with 2 parrots it got. It has never seen parrots, this thing. It's only seen circles and lines floating around and explosions, and this is what it has seen. Okay, it makes some mistakes. I don't know why this, but still one person eating lobster, but the rest, well, the one's showing a lobster, and the rest is kind of random. But I mean, the neighbors are pretty good, and this is this is not just that ImageNet is easy. Like this is from ObjectNet. ObjectNet is another dataset that was created to make ImageNet perform really badly. So anything that you train on ImageNet should perform really badly here because they chose things that will have like random orientations in 3D and so on. So what I'm showing you now is the nearest neighbors for some images here. These are the nearest neighbors when you use shaders for training. Okay, performances are really bad, okay, because now this dataset is crazy, it's really difficult. But the neighbors are really nice, no? I mean, here, for instance, I think it's matching the carpet, really. So the category is wrong because that was not the category of this image. But the neighbors are really nice, no? It's looking at boxes. There are, you know, many of the images just look very interesting. Like here now, there is a hand, and there appear some hands. You know, it's just quite amazing the fact that this thing has never really looked at real images. And what has the network really learned? So you can look at what the units are doing. So this is what one of the units in one of the last layers has learned when it's trained with shaders. So they really learn about texture. So this unit seems to be selected. So these are the images that most strongly activate that unit. And it just seems to be selecting some random texture. Here there is another unit. It's just shapes and texture. There is really nothing meaningful in these units. This one seems to detect isolated objects on a flat background. And then there are, you know, other units that detect like circles, some more texture, like bright things against a dark background. There is no semantics. If you do the same thing and you supervise with ImageNet or with, you know, with other datasets, you actually see units that are selective to objects. You don't find this here. It's just textures and shapes. But those features seem to be rich enough to support classification. So, you know, what I think is maybe the evolution of computer vision datasets. Maybe it will look like that at some point, where this really represents the amount of real images that we need. This doesn't mean that you don't need images, but most of them could be just fake. And I don't mean like synthetically generated, like with a virtual environment. I mean, you know, these crazy processes that just generate things that look like nothing like real, where the gap between simulations and real is huge. Okay, but that's fine. Okay, so I have a stopping point here. I don't know. I'm out of time, so this is it. You know, I finished here my presentation.
All right. Well, as promised, Antonio can be relied upon to twist your brain in all the weird directions. Questions? Yes.
Thank you. Yeah, like I was asking about the videos. Like I'm wondering if you have relied on the historical information of the, like, for example, the former frame and the next frame. There will be a relationship between them. So I only.
Yeah, you can. Yes, we use that. We can use that, for instance, when you are doing the supervised, the contrastive learning, by making sure that, you know, they have to be far away temporally, because if they are close temporally, they might still be neighbors, no? So you put some time between them, so that the frames look relatively different. Yeah.
One more, sorry, like.
Here.
What's
Make
this?
it short, please.
Oh, sure. Thank you. I think like you are sampling logical imagery from noise, right? But I'm wondering how you can like pick out the positive and the negative samples to finish the training process.
Oh, but here we use the exact same thing that you do in contrastive learning. The positive examples are given one image, transformations of that image, you know, small augmentations, and the rest are negative examples. So we don't really change anything on the training procedure. Everything is as if you had real images.
Very interested. Thank you.
So it seems like you have created something from nothing. And I'm trying to find where's the pitfall.
Okay.
So one of the things I noticed on your vertical axis is that the accuracy was never really that great. I mean, you were hovering around 50%. How am I to understand what you've done?
Well, okay, so 50% is still pretty high because chance is 1%. So I think this is a hard classification task. So I think 50%
you
is.
still have to tell me how you created something from nothing.
Well, you know, I think that comes back to what Jitendra was saying before. It's not from nothing, no? It's from all the cumulative knowledge that we have from computer vision history about what things seem to make sense to produce images that look realistic, no? And all this has been relying on types of generative processes that people have, imagine in order to explain properties that we know are present in natural images. That Leaves model was used to explain why you had a correlation between pixels that was, related to the 1/f power spectrum. So that was one model that tried to explain what that property might come from. It was used to create models like Retinex to separate luminance and shape. So people have been working quite a lot of time on this type of model. So we know that we were not following a path that had no future. Like I thought that with I was sure that Deadlifts was going to be able to do something. It's just that, and the beauty of the game is that it didn't really matter where it landed. So it was a win-win situation for sure. It can be here or here. It doesn't matter.
Other questions? Okay. No, don't give him that one. You need that. Okay.
Hi, Antonio. Thanks for the great talk. So I feel like going n equals 0 this way is following the word of the law, but not the spirit of the law. Have you thought about what happens in low compute with these images, where you actually don't train for 100,000 images?
Or if you have fewer images.
You have fewer images that are either synthetic or some other.
Yeah. So I mean, then you have the same properties that you have with real images. That as you add more and more data, you get better and better and better. Then it will saturate at some point. So 100,000 images is what we could use to get to the deadline.
I see.
That's generally what limits you. So in fact, we plotted the performance as you add more and more data, and it didn't feel like we were at maximum performance yet. So, but because the trends at the end, they don't really change the ranking. So you have to decide at some point to stop.
You can imagine that as it saturates, it might change the ranking.
Yeah, but it's very difficult to believe that something is going to progress very, very slowly but forever. Generally, these things kind of move parallelly. I mean, it might be different, but we observed that it was starting to saturate. So it's not like we were still far away. We were starting to see some saturation. So maybe the saturation will have happened with twice or 4 times the amount of data that we used. But I don't think that it will have supported a lot more.
There's a question back here.
Thanks for the great talk. What happens if you combine the synthetic images with natural images?
Oh,
Does it
okay.
have any benefits or?
Yeah, okay, that's a great question. And the problem with that is that I think that's great. I think you can do it. I think we did some experiments like that, and really what you see at the end is that the natural images will dominate, and you get very little benefit. The other thing that you can do is fine-tuning. You train with synthetic images, and then you fine-tune with real images to see how far you get. The problem with that, and I don't like about mixing data sets in that way and everything, is that I think it distracts you a little bit from the ultimate goal, which is to have a process that is completely blind to real images and see how far you go. As soon as you add the dimension of adding more real data and see what happens, then you go through a rabbit hole that it will distract you, and then you'll. Sorry?
And it's no longer 0.
Yeah, and there's no longer 0, so you cannot give this talk, for instance. No?
What was the story with the scattering transform? Where did it land?
Oh, so the scattering transform. So it actually performs really well. It just gives a much high. It's a very high dimensional vector at the end, and I don't think we did the experiments with this particular data set, so I don't know where it lands here. But it was actually not too bad.
Maybe one last question. Oh,
There is.
Video.
What?
Video.
With me?
No. Video.
Oh, video.
Instead of static images, suppose you
Oh.
had time.
Yes. Yeah, I think that it's particular with the shaders. No, you have all the information, and even with the lifts, you can add, you can make them move.
The dynamic models are easier than the spatial models.
Yeah, but at the end, I think it's just a question of computational cost, and we decided to start with this. But I think a video will be great. I think that for video will work really well.
Yeah. Oh my.
Yeah.
Okay, I get to the last question.
Okay, sure.
The ordering of the fine tuning, or the linear layer, and the ordering of nearest neighbor, are they the same orderings?
Sorry, what?
So you have also nearest neighbor, like you can evaluate using
Oh,
nearest
yeah,
neighbor.
it's the same thing.
The same order.
Same
Okay.
ordering, yes, yes. I mean, there are maybe some small swaps locally, but it's basically the same ordering, yes.
All right. All right. Well, let's thank the great Torralba once again. So actually, Antonio will be around tomorrow morning and Friday morning. If you really want to chat with him and you didn't have a chance, there might be some possibilities in the next 2 days. Okay, thank you very much.
Thank you.